Hello and welcome back. The topic that we'll be covering this week is the Niagara Escarpment. Many of you might be familiar with the Niagara Escarpment as the place where the Niagara River flows over at Niagara Falls, but it's actually a really intensely long land feature that stretches all the way from sort of New York State, kind of through southern Ontario, across the southern part of the Georgian Bay, and then back down into Michigan. We'll be looking at things like the origin of the escarpment and some escarpment processes. So in this map we can see the extent of the escarpment in this little red line. It actually sort of hugs a lot of the sort of curvilinear shape of a few of the Great Lakes. So as I said, it starts in New York, down here, New York State, curves around Lake Ontario, all throughout southern Ontario. It skips along the bottom of the Georgian Bay, Manitoulin Island, before curving around the outside of Lake Michigan. And what the escarpment is essentially a series of cliffs. And that's because of really how the escarpment came into existence. It's fundamentally related to a specific rock unit that is found around the edges of something called the Michigan Basin. And the Michigan Basin is basically a bowl-shaped collection of sedimentary strata. So it's a particular type of basin called a dynamic basin, which is created due to convection in the mantle of the Earth. So it just so happens that there's a little bit of mantle underneath the Michigan Basin that, for a long period of time, and possibly still continuing today, is kind of sucking downwards towards the core. So what that means is, if you're pulling a string, the crust is actually deforming downwards over time. So it's a little bit of a warping in the crust. And as it continues to just warp downwards very slowly over time, it gets filled successively with new sedimentary layers. And each of those layers, they reflect different environmental conditions, but we don't really need to go into that right now in order to understand the origin of the escarpment. On this figure on the right, the colorations refer to ages of rock, and the one that we're interested in terms of forming the Niagara Escarpment, is that boundary between the dark purple and the light purple. So I'll just trace it with my mouse here. Again, it curves all the way around Lake Huron and around Lake Michigan. So these rocks are roughly Ordovician in age. I'm going to play this little animation now, which demonstrates those basin-forming processes. So what's going to happen is first you'll see the crust start to bend inwards, and then there'll be a period of erosion that's just going to plane across the top of all those layers, and what we'll see as a result is this bullseye shape with the youngest sediments in the center and the oldest sediments towards the outside. So each layer kind of fills in the gap. Okay, and now it's going to start to erode. We'll see a little plane of erosion just wearing right down through these layers until we get a bullseye shape. And there we go. So in Ontario, we're kind of at the northern part of this rim. So you can imagine that if we were walking across this plane of erosion, if we were walking towards the south off the Canadian Shield, towards the center of the Michigan Basin, we would be going from older rocks exposed at surface to progressively younger and younger and younger rocks. And that's effectively what has been going on for, the last at least 200 million years, is erosion of sedimentary rocks and backwards retreat of the escarpment, because all the escarpment is basically the edge of a particular unit of very tough resistant rock. So in this animation, we'll show the retreat of the Niagara Escarpment. And what I've tried to show here is that the escarpment is kind of quite a cliffy unit because it's so resistant, while some units, like the green one and the brown one, are what's called recessive. So instead of making a cliff when they are eroded, they make a slope. And I know that's very fine detail, but hopefully you can kind of see it in this video. So just the backwards retreat of the Niagara Escarpment over time as it wears away. It exposes older and older units underneath. But even though we can kind of imagine the rim of this basin around sort of a bowl-like shape, we also have to think about other factors that might be warping the shape of that edge just a little bit, sort of making it slightly undulate. And those things are things like the Algonquin Arch, which is a little bit of a high-lying area between two basins, so between the Appalachian Basin to the east and the Michigan Basin itself. We also have the Frontenac Arch towards the north. These are just places where the underlying Precambrian rocks are actually just flexing upwards, just a very slight, tiny amount. So on this topographic image, we can kind of see that the escarpment itself is highest, sort of down south of Georgian Bay in places closer to like Orangeville, for example. And then as you move towards the tip of the peninsula, it slopes very gently down, finally towards the water, and then finally it actually goes underwater. And the place it goes underwater is, of course, at Main Channel, which ends up connecting Lake Huron over here to Georgian Bay itself. We can still see the general topography of the escarpment. It still exists underwater. It creates all sorts of navigational challenges, and it creates really good scuba diving, for example. But it's just a little bit too low to sort of keep above the lake level currently. As we go into Manitoulin, the escarpment gets a little bit harder to define, perhaps. It actually runs along the southern edge. Some of these cliffs are Niagara Escarpment. Okay, so what makes the escarpment itself? The reason why it exists is because it's effectively quite a prominent, thick layer of hard rock on top of a thick layer of soft rock. So the hard, and this is a phenomenon that is replicated many times in geology, and also many times in Ontario. So although the Niagara Escarpment is the tallest set of cliffs that we have, it's not the only escarpment. Generally what happens is you have some sort of rock type, like limestone or dolostone, which is extremely well cemented, which means it's fairly homogeneous. When it breaks into really large pieces, and it's sitting on top of a layer of relatively soft rock. And actually the height of the cliff is largely more controlled by how much soft rock is underneath than how much hard rock is on top. So we call that hard rock a cap rock, is a sort of general term. Well, the soft rocks underneath that are very prone to erosion, we say are recessive, which means that they erode more easily, or weather more easily. This is actually just a beach analogy from just near Collingwood, but I think it shows fairly well. We have a layer of either limestone or dolostone sitting above a layer of shale. Limestones and dolostones are very good cap rocks. Things like shale or anything that has a lot of bedding in it tend to be very poor cap rocks, but tend to be more recessive. And so we can see that the shale breaks into just tiny little fragments. Anytime a storm comes along, it's going to eat away at that shale. It'll get transported really easily. Whereas all of these sort of larger big boulders that we see are basically made from that more resistant cap rock unit. And this is the same process that governs, particular types of waterfalls. This is an example where we have shaly rock lying underneath the dolostone. And the dolostone ends up protecting the shale from the erosion of the water moving over this slope itself. So if this dolostone weren't there, the shale would easily become an actual sort of sloping unit. It would just make a sort of gentle slope profile, rather than having this sort of sudden drop that we see that makes a nice waterfall feature. So of course, whether we have hard rocks or soft rocks relates to the geology. And in these figures, we try to demonstrate what the different rock units are that create the Niagara Escarpment. And the ones that are important for us are the Amabel Dolostone or the Amabel Formation. Either is fine, because that is the cap rock. And actually, the Guelph Formation above it is also dolostone, it's also fairly resistant, but the Amabel Formation is directly above quite a thick sequence of various formations that are somewhat more recessive. And on this little column that we have, the stratigraphic column on the left-hand side, the thickness of the column is attempting to indicate how strong those rocks really are. So we don't have to worry about the origins of these formations. It's sufficient to say that they are different in character because of the way that they formed when they were first laid down and what the environmental conditions were. But for now, it's sufficient to say that things like shale and limestone tend to be more recessive than things like dolostone, which are the cap rocks. So we can see that this entire package of sedimentary rocks is just slightly dipping or sloping towards the south, which of course is towards the center of the Michigan Basin. And if we trace the edge of the Amabel Formation, that essentially gives us that line of cliffs that makes up the escarpment face. But the reason that the escarpment is so high is because we have that really resistant unit over such a great thickness of more recessive lithologies. This is a great example here. We have Manitoulin Island. We have three formations, the Amabel, the Clinton Cataract Group, and the Georgian Bay Formation. The Amabel Formation is our tough cap rock, and one of the most famous landmarks on Manitoulin Island is a beautiful hike called Cup and Saucer. You can go and hike up here, it doesn't actually take very long. Walk along this really sheer cliff front, this really sheer cliff face. And if you look very carefully at the map, it's this little dot of pink amongst basically green. And that pink is a tiny little outlier of Amabel dolostone protecting the Clinton Cataract Group underneath. All right, so I think we've sort of covered the basics of why we have this cliff face and why the cliff is kind of a curved shape around the edges of Lake Huron. But something else we need to take into account when we're thinking about the origins of the escarpment is jointing. And what jointing is basically just cracking of the rock. It's much different than faulting, because when you have a fault, you have two sides of rock that move in different directions from each other. Here, there's really no displacement. The rock is staying whole, it's just cracking a little bit. An analogy might be if you were to, take a cracker and then just sort of flex it a little bit, it might break into a couple different pieces. We can see on the right what jointing looks like. Usually they are very regular, kind of evenly spaced fractures. Because they're fractures, water tends to get in there, and dirt tends to get in there, and plants tend to grow along them. So quite often they're sort of aligned with things like vegetation. In this bottom image, again, we can kind of see this cross-hatched pattern, and that's because there are several different jointing sets. And the orientation of these joints tends to be very regular over very wide distances. So there are three reasons why jointing could exist today. The second one of these is probably actually the most important, but the first reason is because of, these rocks have been through a lot because they're quite old, and they do undergo sort of gentle warping related to just like really gentle flexing due to things like the Michigan Basin and the Algonquin Arch. And that flexing can cause joints to form in certain orientations. More importantly is probably what is going on in terms of the overall motions of North America today. So North America, due to creation of oceanic lithosphere over at the mid-ocean ridge and the mid-Atlantic ridge in the Atlantic, is getting pushed roughly westwards just at a rate of centimeters per year. And this causes joint sets to form in roughly a northeast-southwest direction. And these are the joints that things like big rivers tend to exploit. And that ends up shaping the escarpment. The third cause of jointing is actually just a stress release from the escarpment itself. Effectively, as erosion happens, rocks are no longer kind of confined in, they tend to expand out a little bit. Rocks tend to breathe if given the space, and as they expand out a little bit, that causes fracturing itself. So I mentioned some big river valleys that exploit certain sets of joints. And that's basically what's creating some of the details of this sort of cuspate shape that we see along the escarpment. It's not just a linear feature. We see that there are big valleys that have been carved into the edge. And these valleys are actually pre-glacial. So they existed prior to the last glaciation, and they are the result of essentially just big rivers running across the landscape. Things like Niagara River, for example, is carving a big gorge into the edge of the Niagara Escarpment. Well, that's true further north as well. So the Niagara River is out of this image, it's quite far south of here, but it's true in the past in these places as well. We have places where rivers at some point were flowing over the escarpment edge and wearing backwards over time. So prior to the Pleistocene, most rivers probably drained actually through something called the Laurentian Channel, which was north of the Niagara Escarpment and sort of ran along the bottom of the escarpment, and it connected this low-lying area of Georgian Bay directly to Lake Ontario. And there would have been big rivers that were feeding down into this larger drainage system. So here we can actually still see what are called paleovalleys, but they have largely been filled in with sediment during the last glaciation. During glacial periods, ice tends also to exploit these reentrant valleys. So as ice moves from north to south, it tends to flow around these headlands, and it tends to sort of shape these headlands into an almost bulleted, rounded shape, while working up through these reentrant valleys and flowing a little bit faster through them. So we also get a lot of sculpting of the Niagara Escarpment due to glacial activity, which flowed against the grain of those pre-existing rivers. So when ice hit one of these, we call them promontories, these areas that stick into the Georgian Bay, the flow of the ice at the base of the glaciers tend to diverge and flow around it. Ice higher up in the glacier might kind of streamline some of the obstacles around the top and carve those into these big geomorphological land features called rock drumlins. And then they streamline the entire promontory into a nice rounded shape. So glacial ice tends to exploit these earlier bedrock river valleys. Another thing that we need to just mention when talking about the shape of the escarpment is that lake level, of course, has changed quite a bit over the last post-glacial period, so between 14,000 years ago and today. And it's dropped about 50 vertical meters. That has important implications in terms of, again, the shape of the edge of these cliffs. So it's just something to remember that between about 14,000 and 12,000 years ago, water levels were maybe 50 vertical meters higher than today. And since then, they've fluctuated up and down. And when we talk about, as we go on to the next section, where we're talking about various processes that are currently active along the escarpment to create some of the landforms associated with the escarpment, we need to remember that lake level has not always been where it was. Sometimes it was actually lapping right along the base of the escarpment. Sometimes it was actually quite a bit lower and extending into the Georgian Bay. So let's go ahead and take a break. And when we come back, we will look at processes that are currently happening to shape the escarpment.